AAVSO would like to offer a heartfelt thank you to everyone who donated to our annual campaign. Thanks to your support, we were able to meet our campaign goal as well as match the requirements for the $20,000 matching challenge grant, which we received. It is your support that keeps the AAVSO thriving, and we couldn't be more grateful. And of course, we would also like to thank and acknowledge our sponsors, Voice Astro and Chroma Technology. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and the technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served include fluorescence microscopy, flow cytometry, biomedical instrumentation and surgical devices, machine vision, multispectral imaging, and of course, everyone's favorite, astronomy. Okay, now it is time to meet your instructor for the day. An assistant professor of astronomy at CalTech, he is a stellar researcher in the field of stellar astrophysics. He studied a wide variety of extreme stellar systems, from pre-supernova massive stars to heartbeat star systems to white dwarf mergers and even more fascinating stuff. In order to do this, he uses asteroseismology, an extremely powerful method through which a single light curve can be used to measure a star's mass, its radius, its age, and more to an astounding degree of precision. Today, we are extremely fortunate to have him online with us, ready to give an overview of the astroseismic technique and the simple theory behind it. Ladies and gentlemen, I give you Professor Jim Fuller. Welcome.
Okay, thank you, Lauren, for that really kind introduction. And thank you to all of you who have logged in from all around the world to hear this talk. It's really exciting to be here, to be able to tell you about some of the research I do. I think it's really fun stuff, and we're going to learn a lot today. So let me just share my screen, get this going. Sorry, I'm going to stop this because I have to share some sound with you as well. So I just have to click the right button. Okay. So here we go. Yeah, so like Lauren said, one of the things I study is asteroseismology, which is basically using cosmic music to figure out what's inside of a star. It's very similar to terrestrial seismology, where we use the rumbling, the vibrations of Earth. We use earthquakes to actually figure out what's inside of the Earth. In astroseismology, we use star quakes to figure out what happens inside of a star. I think it was Sir Arthur Eddington, famous stellar astrophysicist, who said that the inside of a star, the center of a star, is one of the most obscured and difficult places in the universe to actually observe, and we'll never be able to see it directly. But using astroseismology, using stellar music, we're basically going to learn why that statement is wrong, and we can basically directly listen to the center of stars, even if we can't see them directly. So today we're going to take a journey to the center of a star, and we're going to listen to some sweet cosmic beats while we're at it, and hopefully learn a little bit of astrophysics. So how do we do this? Well, the reason we can do it is that stars are not just static objects, as you all know. They're variable, they change, they pulsate in brightness, they can do lots of different things. But if you were able to see a star, you'd see something like this. So the outside of the star might change its temperature, and it might change its shape a little bit. It might pulsate radially in and out. But physically, those pulsations at the surface of the star are composed of waves that travel all the way through the star. And there's a few different types of waves, but the most prominent ones are actually sound waves there. Sound waves that travel all the way from the surface of the star into the interior and back out. So the structure of this wave can be quite complicated on the inside of the star. It can kind of make this onion skin-like structure. But at the surface, you tend to just see a very simple pattern. And that's what we basically measure. So of course, we can't actually resolve the surface of a star. They're too small. You all know that. So what you have to do, what you usually do is you just measure the brightness of the star as a function of time. And so if the star just pulsated at one frequency, you would measure the brightness. It would look like a sine wave, just like this. And so, you probably all know that we can't directly hear the stars. You've probably seen movie trailers that say something like, "In space, no one can hear you scream," right? So what we have to do is, of course, measure the photons emitted from the surface of the star. So you can measure the brightness fluctuations. You can do more sophisticated things like take spectra of the star and look how the spectral lines vary with time. But this is the basic technique. And what you can do with that is the frequency of that pulsation will tell you a lot about the structure of the star in many different ways. But I think the simplest concept is just that little things tend to pulsate at high frequencies and big things tend to pulsate at low frequency. And the reason for that is that if you have a sound wave traveling through something, it takes less time to traverse a small object. And so the frequency of the oscillations is higher. So this is demonstrated by any kind of musical instrument. So if you have a little thing like this little violin player playing a tiny violin, you'll get a pretty high frequency stellar song. Okay, so very adorable. So you could think of this tiny little violin player playing a 1/16th violin as maybe like a little star, like a white dwarf star that pulsates at high frequencies. But there's also really big stars, say red supergiant stars that are much more enormous and pulsate at much lower frequencies. So here's a guy playing an octobass. This would be like an analogy of a red supergiant star. So the octobass is a much bigger instrument. So it takes those sound waves much longer to traverse the whole length of the strings. So the strings tend to oscillate at lower frequency. And the same concept is true with stars. So usually when you look at stars, the ones that pulsate at higher frequencies, that play higher pitched songs, are smaller stars. So let's compare pop stars to actual stars. So the vocal range of a really good pop singer like Mariah Carey is something like 100 hertz to a few thousand hertz. So that spans about 5 octaves, whereas stars pulsate anywhere from about 10 to the -8 hertz. That's pulsation periods of about a year, to 1,000 hertz. So that's actually in the same range as human hearing. So neutron stars, which are the smallest stars we know of, those can pulsate at about 1,000 hertz in the human hearing range. Whereas red supergiant stars, those might take a year to pulsate. So stars span, unlike Mariah Carey's, can span about 5 octaves. A stellar symphony could span about 36 octaves. So it's a pretty impressive vocal range that stars have. Although to be fair to Mariah, typical stars only pulsate maybe in 1 or 2 octaves. Their pulsation frequencies typically span a fairly narrow range, but if you add up all the different kinds of stars, they span really quite an enormous range. So it's quite an impressive orchestra. So let's hear some real star songs. What I'm going to play for you is actual data that has been sonified. So it's basically what I showed you before. You measure the brightness of a star for a long period of time, and then you just turn that waveform into a sound bite. So if you do this for a star like the sun, you would hear stellar music that sounds something like this. So you can hear there's a lot of different frequencies in there, right? It's not just one tone. It's quite a complicated sound. Not the most harmonious sound. Stars don't like to play music that falls into one scale. The actual notes are determined by the structure of the star. But if you looked at a star a bit more evolved than the sun, something like a subgiant star that's maybe a few times bigger, you're going to hear notes that typically are a few times lower. So this is what you might hear from a subgiant star. Sorry. Okay, so again, there's several notes. There's some beating going on because basically the amplitude of the notes aren't steady. They're changing over time. And of course, you heard that the sound was a bit lower pitch. If you did the same thing for a red giant star, we'd get an even lower pitch sound. So that's real stellar music. I have had to increase the speed by a factor of 1,000,000 to get it into the human hearing range, but otherwise that's actually real data that's been sonified. So to give you some sense, the sun pulsates mostly at frequencies that are about 5 minutes. So the oscillation periods of the sun are typically a few minutes to 10 minutes or so. Whereas if you go to red giant stars, or these are fairly low luminosity red giants, those periods will increase up to a few hours. You go to the biggest red supergiant stars, those periods increase all the way up to a few years. So how do we actually learn anything from this, right? So the way we learn is because stars actually play a whole spectrum of notes. So if you in this animation I showed before, the star is just pulsating at one frequency. And so if we measured the brightness as a function of time, we would just get one frequency, and so we'd get one note. But luckily, real stars don't just sound like this, right? If this is what a star actually did, the sound of the star would be very simple. It would just be one tone. It would sound like this. So that's a pretty boring song. Luckily, stars are a bit more interesting than that. They have timbre. In other words, they pulsate at many different frequencies at the same time, and so you get a more complicated sound. So if we measured the brightness of a star that's pulsating at 2 frequencies at the same time, we might see a pattern of brightness that varies as a function of time that looks something like this. And what we like to do as scientists is take this measurement of brightness as a function of time and take a Fourier transform or power spectrum and measure the intensity fluctuations as a function of frequency. So in this case, you can see there's one low frequency sine wave here that would produce this low frequency peak in its power spectrum, and there's a high frequency oscillation here that would produce this high frequency peak in its power spectrum. And so stars do the same thing, except typically it's many different frequencies at the same time. If we listen to the sound of this star, this fake star that plays 2 notes, sounds like this. You can probably hear 2 different pitches there instead of just one. But typically stars pulsate many different frequencies. Sorry. Give you a more realistic sense of what a star sounds like. It has more timbre, it has more structure. Think about 8 different notes at the same time. And so you hear a lot of different things going on there. And the same is true with stars. So if you actually look at the brightness of, say, a red giant star as a function of time, you might see something that looks like this. So this is real data from the Kepler satellite. This was a very powerful space mission launched by NASA about 13 years ago now. And basically what Kepler did is it just stared at 100,000 stars continuously for 4 years, and it measured their brightness every 30 minutes. And so if you put that data into a plot, the brightness of a red giant star would look something like this, where it tends to go up and down on a time scale of hours. And all this structure you see here is real. I mean, it looks like noise, but really these are the actual stellar pulsations. And it's quite complicated, right? This is not a simple sine wave. There's actually many different frequencies at the same time here. So one thing that you'll notice also is the amplitude of these pulsations is quite small. So this red giant star, the pulsation amplitudes are about 10 millimag, so that's about 1%. So this kind of stuff is pretty hard to observe from the ground, right? Because stars twinkle, and so it's hard to measure this small scale of amplitude fluctuations. As you all know, there are some stars that pulsate at much larger amplitudes of order 100%. But some of these stars, the signals that we're looking at are actually quite small, and that's why it's very difficult to do without a space telescope. So if you take brightness as a function of time like this, and take the Fourier transform, like I mentioned before, and you plot this in a power spectrum, what you'll see is that that data, which looked like a big mess, actually gives you this very regular ordered spectrum of peaks in the power spectrum. So in other words, each one of these peaks corresponds to a different note that the star is playing. You can think of the star as a big instrument, a big piano or something. These are all the different notes that the star is playing. And each one of these peaks corresponds to a different mode, a different oscillation mode, which corresponds to a different spatial structure inside of the star. So you'll notice that each one of these peaks is labeled by a number. Some are 0, some are 1, and some are 2. This corresponds to the angular structure of the pulsation. So the peaks labeled 0, these are called radial oscillation modes. And physically what that means is basically the whole surface of the star at all angular coordinates, at all latitudes and longitudes, is moving in the same way. So a radial pulsation is physically the surface is moving in and out. And same with the inside of the star. It's basically each shell of the star is just moving in and out. The peaks labeled 1, these are called dipole oscillation modes. And these are characterized by a spatial pattern that's asymmetric across the star. So basically one side of the star is moving in one direction, the other side of the star is moving in the same direction physically. So basically that would correspond to the surface of the star moving back and forth. So it could be up and down, or it could be side to side in a circle, but that's basically what a dipole oscillation is. And then a quadrupole oscillation, which are these peaks labeled 2, that's when you take the whole surface of the star and you squish it back and forth. So basically squish it from a sphere into a rugby ball and back. So this movie I played for you before, this is a quadrupole oscillation, because you can see what the star is doing at the pole here is different from what's going on at the equator, and that's again different from what's going on at the other pole. So this is an example of a quadrupole oscillation. And typically the only ones we can see are these radial oscillations, dipole and quadrupole, 0, 1, and 2. You can see there's some little peaks labeled 3. Those are called octupole oscillations. That corresponds to these more complicated patterns these are all spherical harmonic patterns. And the more complicated patterns are hard to observe because you start getting cancellation on different parts of the star. So you'll notice, this part of the star, which might be dark, would cancel this part of the star that's bright. And so the integrated brightness fluctuation of the whole star is very small. And so that's why those more complicated patterns are harder to observe. But there's still a lot we can do with these peaks. You see that there's some very nice regular structure here. You see you have a quadrupole oscillation right next to a radial oscillation. And then that pattern repeats with a characteristic frequency spacing, which we'll talk more about. In between, you have one of these dipole oscillations, and that pattern also repeats. So physically, what's happening in this pattern is, even though each one of these dipole oscillations has the same angular structure, the radial structure inside of the star is different. So each one of these successive peaks basically has one more onion skin if you look at its structure inside of the star. So for instance, in this graphic here, you can see there's about 6 different oscillations. You go from red to green and back again about 6 times in this particular graphic. And that's what's going on here as well. This might be a peak corresponding to, say, the 6th harmonic of the stellar oscillation. This might be the 7th harmonic, the 8th harmonic, etc. And so that frequency spacing is basically going to end up corresponding to how long it takes a sound wave to travel through the star. So we can learn a lot by measuring that. So to give you some sense of physically what's happening here is you can think of the star as sort of always rumbling. Unlike the earthquake, where we have to wait for individual earthquakes, stars are constantly shaking. And the reason is they have convection going on at their surface. They're like a big boiling pot of water. And so they're always kind of rumbling around at low amplitude. So what that means is there's always sound waves that are being excited near the surface of the star by that convection. And those sound waves physically actually travel all the way through the star to the other side of the star, and then they keep bouncing around. And it's the same way that seismic waves propagate through the earth after an earthquake. So some of those waves basically only propagate in a little ways and refract back out. But some of them really propagate all the way through the center of the earth and emerge on the other side of the earth and then keep doing that. The same thing is true of stars. So if you actually mapped out the path that an individual sound wave would take as it traverses through the star, for the oscillations of the sun, they would take a path that looks something like this. So basically the sound waves, they're excited at the surface, they start propagating towards the center, but because the sound speed is higher at the center of the sun than it is at the surface, the wave gets refracted and it comes back out towards the surface again. And so then once it gets to the surface, it reflects. This is similar to a sound wave reflecting off of any kind of surface that has a sharp discontinuity in it. And then it travels back through the star and back out again. And so the actual path taken by an individual sound wave would look like this, but the structure at the surface of the star would be, can be any one of these spherical harmonics, like I said before. So that's what happens for stars like the sun. So this top panel, again, is a power spectrum of a sun-like star. And there's this nice regular pattern because all the waves that we see in the sun are sound waves. And so basically, the star is just playing one scale, and each note is kind of the higher, the next octave up in the scale. You could think of it like that. But some stars, like red giants, actually have a much more complicated structure, and they have a much more complicated pattern of notes that they play. So in this bottom panel, this is the power spectrum of a red giant star. I'm going to try to move my sound bar so you can see it. So here you see that there are many, many different peaks in this power spectrum. Again, each one of these corresponds to a different oscillation mode of the star, which is like a different note. But now there's many more different peaks in the power spectrum. And that's because there's actually 2 types of waves that propagate through red giants. There's sound waves that propagate through the surface layers. And there's actually a different kind of wave called a gravity wave, which is like a buoyancy wave that propagates through the core. It's kind of, you can think of it similar to a wave that propagates along the surface of the ocean, right? That's not a sound wave, it's a different kind of buoyancy driven wave. And the same kind of waves propagate through the cores of red giant stars. And it turns out that the oscillations we see are kind of half and half. They're half sound wave, half gravity wave. And so this gives it this power spectrum a much richer structure. So the timbre of this star would be much more rich, be much different sound if you could hear it. So to give you an idea of what's happening, if you looked at a wave that propagates through a red giant, it would take a path that looks something like this, where at the surface of the star, it takes a path corresponding to a sound wave. But in the core of the star, it actually takes this tightly wrapped kind of spirograph type pattern. And that's the way that a gravity wave propagates through the star. And these gravity waves actually go all the way through to the very center of the star and back out again. So when we see these stellar pulsations, we're really getting information about the structure right at the very center of the star. And this has allowed us to do all kinds of incredible science that we couldn't do until we were able to observe these oscillations. So let me give you an example. So again, this is this power spectrum of a red giant star. And let's look at these peaks labeled L=1 here. So you see that there's these groups of peaks labeled L=1. Each L=1 group is actually split into 3 peaks, and we'll talk about that in a second. But then the L=1 groups, they kind of repeat with the characteristic spacing, which you can see here. You can see it again here. Here's an L=1 group, here's another one, here's another one. And so this spacing between different L=1 groups, that's what's called a period spacing. And it turns out that that spacing tells you a lot about the core structure of the star. So one of the things that we've done, because we have data like this for thousands of red giant stars now, is for each one of these red giant stars, we measure what's called the frequency spacing, and that's basically the spacing between these successive L=0 peaks. We measure that value, and then we also measure the spacing between the L=1 peaks here, and that's called the period spacing. So we do that for thousands of stars, and then we put them all on a plot like this. So each one of these points on this plot is a different red giant star, where we've measured the frequency spacing between the L=0 modes. That's what's on the x-axis. And we've measured the period spacing between the L=1 modes. That's what's on the y-axis. And you can see that the stars fall into these very different groups. So this group of stars on this lower branch, these are what's called red giant branch stars. These are stars that have burnt all of the hydrogen in their cores into helium. So now they have just a dense helium core that's pure helium. And then around that, they have a hydrogen burning shell. And those gravity waves that I was talking about basically propagate all the way through, all the way to the center of the star and back out again. And that gives you some characteristic period spacing. If you look at these stars, these are actually stars that are burning helium in their core. And so right at the center of the star, you actually have convection, where helium is being burnt into carbon and oxygen. And that convection zone prevents the gravity waves from propagating all the way to the center of the star. And so the period spacing that you get between the different modes is different. And so it falls into this different branch. So these kinds of stars, you know, these stars here and these stars down here, they would look almost identical at their surface, but their core structure is quite different. And the only way we can tell the difference between these two different classes of stars is using this asteroseismology. So this has been one of the really powerful developments that has come along in the last several years by being able to listen to the sounds of these stars. So there's even more complicated things you can do. So I said before that those L=1 groups of pulsations, they're actually split into triplets here. And the reason for that is that for an L=1 spherical harmonic, you have 3 different M values, and those basically correspond to one type of oscillation that's going up and down around the rotation axis of the star. And then this higher frequency pulsation is basically a pulsation that's traveling around the equator of the star in the same direction that the star is spinning. And so because of the star's spin, it gets Doppler shifted to a higher frequency. Whereas this pulsation is a wave that's going around the equator of the star in the opposite direction. So it gets Doppler shifted to lower frequency by the spin of the star. So we can actually measure the spin of the star by measuring the spacing between these different peaks here. And even more than that, we can actually do this for different oscillations that propagate through different parts of the star. So this particular oscillation mode is one that's mostly propagates at the surface of the star. This particular oscillation mode is one that's more confined to the deep interior of the star. And you can probably see that the spacing here is larger for this mode than it is for this mode. And so physically what that means is that the core of this star is actually rotating faster than the surface layers of the star. So we can actually measure the rotation rate at different depths within the star, which is really exciting. And that has allowed all kinds of new developments in understanding the physics of stellar interiors. That's one of the things I've worked on quite a bit. Another thing I've worked on quite a bit is actually using this data to measure magnetic fields inside of stars. This is something we've never been able to do before. And the reason you can do that is actually, it turns out that some of these red giant stars, basically some of their notes are just muffled. It's like if you took a piano and just cut a bunch of the strings so that the star couldn't play as many notes. That's what some of the red giants look like. So up top here, this is a power spectrum of a normal red giant branch star. You can see these dipole modes are shaded in red. But some stars, about 20% of the red giants, the dipole modes are just gone. You still see the other modes, but you don't see the red peaks anymore. And so what's actually happening in those stars is, remember, it's these dipole oscillations that are the ones that really propagate all the way to the center of the star and back out again. So what's actually happening is these waves are getting damped out. They're getting muffled inside the core of the star. And so that basically prevents the star from playing that note. And we know that what's doing that is magnetic fields. Actually, it turns out that when a wave encounters a sufficiently strong magnetic field, it basically disrupts it. It prevents the wave from going back out to the surface of the star again. So we don't see the star pulsate in that frequency anymore. And so we've actually been able to measure magnetic fields inside of stars just by measuring their brightness at the surface. So it's been really fun developments over the last few years. So in the last bit of this talk, I'm going to talk about some other types of stars that pulsate. One of my favorite types is what's been called heartbeat stars. And the reason these are called heartbeat stars is if you just measure their brightness as a function of time, it kind of looks like an EKG diagram like this, where you get this kind of sharp peak or this beat that occurs every once in a while, and maybe some oscillations in between the beats. And what these are actually stellar duets. They're actually binary stars that orbit each other. And every one of these peaks here in their brightness corresponds to when the stars pass close to each other. So these are stars in eccentric orbits. Here's a movie I made of one star system called KOI 54. It has two stars that are almost identical, but they're in about a 42-day orbit. Every 42 days, they pass very close to each other because they're in an eccentric orbit. And when they pass close to each other, their light reflects off of each other, so you get a big spike in their brightness. But the other thing that happens is the stars get so close to each other that they actually gravitationally distort each other, and they keep kind of oscillating after that. It's like the two stars are a bell, and they kind of ring each other every time they pass by each other. And so they excite oscillations in the star that we again see in the data for these types of stars. So if you actually listen to the sound that this type of star would make, again, you have to increase it by about a factor of a few million to get it into the human hearing range. But you'd hear something like this. So you can basically hear two main sounds here. There's kind of one high pitch frequency, which corresponds to the oscillations of the star throughout the orbit. And then there's also a beat, and that basically corresponds to this spike in brightness when the stars pass closest to each other. So this is pretty typical of heartbeat stars. So this is actual data, again, from the Kepler satellite. This is the brightness as a function of time of one particular heartbeat star system. So again, there's basically one dominant frequency that happens throughout the whole orbit. And this is one of these tidally excited oscillations. And then there's this beat that happens at periastron. So this particular system has a slightly different sound to it. So there's kind of a different ratio of the tone to the beat. But you get all kinds of different sounds for different kinds of systems, depending on their eccentricity and the actual sizes of the stars. And so this is one of the things I've been working on modeling. Here's a different one. This one actually, well, I'm only showing part of the data here. This particular system actually oscillates 229 times each orbit. So the sound it makes is a little bit different here. You can still hear the beat, but it's much more faint because it only happens every 229 oscillation cycles. And so we get, just a whole bunch of range of these things depending on their binary configuration. Here's one, you might want to cover your ears. This one is not quite so harmonious, and the reason is this one only oscillates about 5 or 6 times per orbit. So in that case, we get 2 different notes that are both in the human hearing range. It doesn't sound so nice because it doesn't fit on a nice scale that we usually enjoy in music. So we can learn all about the evolution of those binary stars by understanding those pulsations. Sometimes in binary stars, you get even stranger behavior. So recently I've worked on these stars that are called single-sided pulsators or tidally tilted pulsators. If you measure the brightness as a function of time for one of those things, it would actually look like this, where this is actually a binary star that orbits each other. And at certain orbital phases, you get large amplitude oscillations. And at certain orbital phases, you get really low amplitude oscillations. And what we've learned is the physical cause of this is that the oscillations, the star, are actually aligned with the location of the companion star that's orbiting. So if you could image one of these star systems, you'd see a pattern that looks something like this, where you see hot and cold spots around the star. These are the oscillations of the star, but they're aligned basically with the orbit of the companion star. So as the system orbits, you're seeing different parts of this pulsation at the surface of the star. So when you're looking at this phase, you actually see, either a red spot or a blue spot. So that means you'd see a large amplitude pulsation. Whereas if you look at the star from the back end, you'd see both a hot spot and a cool spot. And so those would cancel each other out. So you'd actually see a very small amplitude pulsation at this phase. And so this is a new phenomenon that was just discovered a couple years ago. If you listen to one of these stars, it would make a sound that sounds something like this. So it's sort of one tone, but it oscillates an amplitude. Physically, that's basically because we are seeing one note in the star, but its amplitude is changing through different parts of the orbit. So I've just got a couple more types of systems to talk about before we wrap up. All those systems have been duets. We also have trios and quartets. So one example is there's a really fun system called the Trinity system that I've worked on setting. This is actually 3 stars that orbit each other. So you have 2 little stars that orbit each other about once every day. And that pair of binary stars orbits a red giant star about every 40 days. And it turns out that in this case, the orbital motion of these 2 little stars around their center of mass, that actually causes gravitational fluctuations that excite pulsations in the red giant star. And those pulsations are at different combinations of this orbital frequency and the longer orbital period. And so we get kind of a very complicated sound in that case. We also see pairs of basically 2 heartbeat stars. And so each pair of heartbeat stars also orbits each other. And so this would be like a quadruple star system. And in that case, when you take the power spectrum, you see something that's very complicated like this. But one thing you'll see is there's this one kind of constant frequency spacing, and that's due to one system with a short orbital period. And then you also see this larger frequency spacing. Sorry, this small frequency spacing, that's the system with a long orbital period. You also see a large frequency spacing here. That's a different binary star system with a longer orbital period. And all 4 of those stars orbit around each other. So you can get very complicated stellar symphonies. And this isn't just limited to stars. So planets oscillate too. I already mentioned the Earth. Of course, we've been listening to the Earth's oscillations for a long time. Another thing that's happened in the last 10 years is we've started to actually be able to detect pulsations of Saturn. And at the time, this was the only planet we'd ever detected pulsations from. And the reason we could do it for Saturn is that actually Saturn's ring systems act like a giant record player that actually record the oscillations of Saturn. And so what happens is as Saturn pulsates, that distorts Saturn's gravitational field. And that actually causes the orbits of ring particles to be perturbed. And so what happens is the oscillations of Saturn actually excite waves that propagate through the rings of Saturn. And we can see those waves, and thereby we can measure the oscillation of Saturn itself. Even though we can't see Saturn oscillating, we can see its effect on the rings. And so this has allowed us to do seismology of Saturn. And what we've actually learned from that has been quite profound. We've learned that Saturn has this big, stably stratified region inside of its deep in the interior. So it's not just a big convective ball of gas, which is the kind of standard picture people have been thinking about for giant planets for the last few decades. Actually, the structure is more complicated. You get this stable layer that allows gravity waves to propagate through it. Those are the same types of waves that made the very complicated structure in the red giant stars. And the same thing is happening in Saturn, basically, that we're seeing those gravity waves. And we're seeing the impacts of their gravitational fluctuations on the rings. So we've been able to do some amazing work on giant planets as well. So that's everything I wanted to tell you. I just want to leave you with a nice little cosmic orchestra here. This is going to be kind of a layering of many different stellar oscillations on top of each other. So let's listen to this, and then I will take questions. Okay, thank you everybody for listening. I'd be happy to take some questions now.
Thank you so much, Professor Fuller. That was an excellent presentation. I knew a little bit of astroseismology going in, but I'm still just in awe at how much there is to learn.
Yeah, there's really a lot we can do. That field has really expanded a lot in the last 10 years.
Fantastic. Okay, our first question here comes from Bradley Walter, who asked a really great question. So these pulsations and these oscillations in the star, what's actually causing the star to become brighter and dimmer due to them? Is it density variations?
That's a great question. So there's a few things that go on. Let me just take you back to one of the videos. Because the star has these sound waves propagating through it, those sound waves basically compress part of the star and make it hotter, and they rarefy other parts, and those parts get cooler. Mm-hmm. And so the main effect that we see at the surface of the star is some parts of the star are hotter. So you could think of this red region as a hot part of the star, and some parts are cooler. And typically you see more of one than the other. Like in this case, we'd see more of the red than the blue. So the star would be brighter at that phase. And then half a cycle later, when you see more blue than red, or more green than red, then the star would be dimmer. So physically, that's the main effect that we usually see, at least if we're using photometry. The other thing that happens is the shape of the star actually changes. Or with the radial oscillation, the physical size of the star is getting larger and smaller. So those are called geometric effects, and those also contribute, although usually at a smaller level than the actual temperature changes. And the third thing we can do, and this is the main thing we do with the sun actually, is we can actually measure the motion, the velocity of the surface of the star using Doppler shifted absorption lines in the spectrum. So that takes a lot more photons because you have to take a spectrum of the star, but there's a lot of photons coming out of the sun. And so that's actually the most effective technique for helioseismology.
Very cool. Actually, now that you say that, I remember we had a webinar not too long ago that talked about an interesting study on Betelgeuse using that technique. I guess Betelgeuse has enough photons that they can just scrape by.
Yeah, I mean, Betelgeuse is one of the brightest stars in the sky, so you can do a bit more with it than you can with most stars. Most of the data I was showing you are from stars that are, you know, 9th magnitude or 12th magnitude or something. So they're, you know, usually you need big telescopes to actually measure the spectrum of the star.
Cool, thank you. Okay, so we had a couple of questions come in about neutron stars and pulsars. So let's take those next. First one comes from Simon Street, who asked, are slow pulsars slow enough that we can get a high enough resolution to see or hear anything useful in that pulse and probe their insides?
Yeah, that's a great question. So pulsars do pulsate, although I cheated a little bit. They don't really pulsate in the same way that the other stars do. So what we see from pulsars are actually radiation coming from their magnetospheres. It's not usually radiation coming from the surface of the star itself. We're just seeing the radiation that's produced outside the surface of the star. And as the star rotates, we see basically the magnetic field sometime sweeping into our line of sight, in which case we get a burst of radio waves, and then when it sweeps away from us, we don't see anything. So the pulsations of pulsars are incredibly useful for measuring the spin rate of the pulsar, and then you can do more complicated things like you can measure how that spin rate is changing as a function of time. You can find binary stars by basically measuring the arrival times of those pulses. But we actually don't get very much information about the inside of a neutron star from those pulses because they're not generated by waves propagating through the inside of the star.
Cool.
Yes, and there's slow and fast pulsars. You can basically, it's the same story for both of those. Some pulsars rotate, you know, several hundred times per second. Those are the millisecond pulsars. And most pulsars rotate about once per second. Those are those kind of slow, normal pulsars. But it's the same story for both of those, that we're measuring something happening in their magnetosphere.
Okay, thank you. So I think that partially answers the next question, but I'm going to ask it anyway. So we had a question from David on Facebook who said, some pulsars seem to have superfluids slushing around on their insides. What difference does that make to their astroseismology compared to something more predictable like a red giant?
I think we would love to be able to answer that question, but unfortunately, like I said, the pulsations of pulsars aren't really due to waves propagating through the interior. So we can't map out the slushing directly. You can try to do more complicated things like maybe the superfluid in the core will somehow affect the magnetic field at the surface of the star. That requires more detailed modeling. It's not really the same as the astroseismology.
Okay, thank you. Speaking of magnetic fields, David had another question, which was a question about, is there a connection between apparent features due to magnetic fields like star spots and flares and stuff like that and pulsations, these astroseismic pulsations?
Yeah, so that's a good question. So there's different types of magnetic fields. So I talked about these stars that have magnetic fields. And here what we think we're actually seeing is we're seeing magnetic fields deep inside of the star. And the reason we think that is that these black and blue pulsations, these are pulsations that are mostly confined to the surface of the star, whereas it's the red pulsations that really go into the deep interior. And it's only the red ones that get suppressed. So what we think we're seeing here is magnetic fields inside of the star that don't exist at the surface of the star. And so you wouldn't actually see, big sunspots or magnetic activity or solar flares. You wouldn't see any of that from this star. Its surface would look totally ordinary. It's just there's magnetic fields in the cores. There are other stars that do have magnetic spots and activity. And it turns out that tends to suppress the oscillations, but this time it suppresses all of the oscillations of the star. So there are some red giants that basically don't pulsate because they have so much magnetic activity at their surfaces that it just suppresses all of their oscillations.
Interesting. Thank you. Okay, next question here comes from John Hoot, who asks, how many millimags is the oscillation in eccentric binaries?
It varies. So the ones I showed you, this is about a 1 millimag oscillation. Maybe you get a few millimags every time the stars pass close to each other. And that's pretty typical for the stars that we observed with Kepler. There are some stars that have been found more recently by test satellites and other surveys like the Ogle survey, where the amplitude gets closer to 1%, or maybe there's some extreme ones where the amplitude is 10% or so. So some of the most extreme ones, I think, could be detectable for ground-based observers. Yeah, there's one system in particular I remember it's actually a massive star in the Large Magellanic Cloud. So it's far away, it's not super bright. But that one, actually, the amplitude of this oscillation gets to close to 10%. So that's something that in principle you could track from the ground.
Cool, thank you. Okay, next question, we have a couple of questions about software. So first, Neil Simmons asks, what software do you use to translate your brightness data into sound?
Oh, so that's actually quite simple. I can maybe send you a script in the chat. I just use Python, and you can basically use Python to transform any data series into a sound bite. I forget the actual name of the function that does that, but it's pretty easy. So for instance, to make a sound bite like this, all I did was I took the actual data for the system and I just fed it into that Python tool. And it's just a couple lines of code actually. And you have to make sure you do it at the right frequency, right? You have to boost the frequency into the human hearing range, but otherwise it's quite simple. So I can paste a little bit of code into the chat at the end of this.
That would be awesome.
Yeah.
I think I know of a package that does what you're talking about. I think it's called Astronify, like Astro and Sonify put together.
Yeah. There's probably more sophisticated things that people have developed. The piece of code I'm using is very simple. It's just like one line of code, and it's not a special astronomy package or anything. Yeah.
Okay. So next question here about software is when you're doing your research, what sort of tools are you using to do light curve analysis?
Yeah, so there's a few different things people do. So I'm mostly a theorist, so my main job is basically letting somebody else reduce the data and analyze it, and then I'm trying to build models to actually learn something from it, to interpret it. So of course there's lots of software tools for, say, reducing the data and taking things like Fourier transforms and Lomé-Scargill periodograms, which are the main tools people use to actually figure out which frequencies the stars pulsate in. And then what I'll usually do is try to then learn from that. And so one of the main things I do is I'll build stellar models. So I use a modeling code called the MESA Stellar Evolution Code. I can use that to build a model of just about any type of star I want, like a sun-like star or a red giant star, or 1 solar mass star, or a 10 solar mass star. It's quite flexible. And then given a stellar structure, we know that those stellar models are not perfect, but they're pretty good. They're probably good to within a few percent. And then once you have that stellar model, you can basically calculate the frequencies at which the star would oscillate. So To do that, you basically take the equations of hydrodynamics and you perturb them. This is called linear perturbation theory. And then you just get a system of equations that you have to solve that basically tells you the frequency and the spatial structure of each one of those stellar oscillations. So there's a different code I use called the gyre oscillation code that I use to calculate those. And then I basically compare those models with data and see, what kinds of models explain what we're seeing.
It's very cool. Thank you. That's a good insight. Okay. Next question here. Oh yes. So could you tell us again how the seismic activity and these sounds are actually being detected?
Yeah. So physically, the star, there is sound in the star. It is a sound wave that's propagating through the star. Mm-hmm. And like I said before, that makes the surface of the star change its shape, and it makes different parts of the surface hotter or cooler. Mm-hmm. And so physically what happens is the hot part of the star radiates more photons because it's hotter. And so the brightness of the star increases if we're seeing the hot part of the star. And so we're just measuring the brightness of the star. That's usually what we're doing. We're just measuring the brightness of the star as a function of time. But yeah, the physical origin of that is a sound wave that's making the surface of the star hotter or cooler.
Thank you. I'm going to add on to that just a little bit, just in case this is someone who's new to the AAVSO. The technique that Professor Fuller is talking about is photometry. That's what we use to measure the brightness of stars. And we do have some information on how you can get started doing that. If you'd like, just go to our website or our YouTube channel and look for photometry information. Okay, next question here comes from James Gage, who asks if the variations are similar at different wavelengths of light, or is there possibly more layers of information if we were to take a multi-wavelength approach?
Yeah, great question. So usually it's pretty similar at different wavelengths. So if you measure the brightness of the star in a red band versus a blue band, it would usually be pretty similar. Mm-hmm. Although there are some differences because the fluctuations are produced by temperature fluctuations, that can basically mean there's a larger amplitude in, say, a blue band versus a red band. Mm-hmm. And in principle, you can use that to actually identify which oscillations you're seeing. There's some work on that. Now, mostly what we've done so far is because the Kepler satellite just had one band. It was just one broad band. It didn't actually measure different bands. We're just looking at the integrated brightness fluctuation across all those different bands. Mm-hmm. But and the test satellite, which is up now, is doing a very similar thing. But in principle, we could, if we did the same thing in different bands, we would get even more information that we could use to help identify which types of oscillations we're actually seeing from the stars. So that has been done by ground-based observers, but we don't have a space telescope that does that for large amounts of stars to very high precision.
Interesting. Thank you. Okay, next question here comes from Bradley Walter, who asks, what effect does a star's spin have on its oscillations?
Yeah, good question. So there's a few effects. The first is just the one I showed in that plot, that basically you have some oscillations that propagate through the star in the same direction as it's spinning. Mm-hmm. So in the Earth, this would mean like a seismic wave that propagates to the east. Right, that would be Doppler shifted to a higher frequency as viewed by somebody outside of the Earth, whereas a seismic wave that propagated to the west would be Doppler shifted to a lower frequency. So that's the simplest effect that rotation has on the oscillations of the star. There are more complicated effects. If the oscillation frequency gets comparable to the rotation frequency, then the physical motions of the fluid particles inside of the star, they feel a Coriolis force, right? So just like currents in the Earth's atmosphere feel the Coriolis force due to the spin of the Earth, the same thing happens to stellar oscillations, and that makes them harder to model. It turns out that mathematically it becomes a much more difficult problem. But there are lots of people who work on that, including my group. That's one of the things that we work on. And so that can also have very complicated effects on the pulsation spectrum of a star. And this is actually something that we know is very important for the planet Saturn. I said that we can detect some of the oscillations of Saturn. It turns out that Saturn rotates really fast. It rotates about a third of its breakup speed, which means it's actually visibly centrifugally distorted. And the pulsation frequencies we see are only a couple times faster than the rotation rate. And so that actually has a really big effect on them. And so you really have to understand that physical process of the Coriolis and centrifugal forces and how that affects the oscillations in order to be able to interpret the data that we have for Saturn. So that's one of the things that my group works on here.
Oh, that's cool.
Yeah.
Okay, thank you. So the next question, we actually have two closely related questions. So I'm going to read them both out before you get to your response. So the first question asks if the planets invoke any oscillations in the sun, or if the sun's oscillations are all entirely internally generated. And the second question asks, given that you've shown some systems where there were multiple objects and there was a measurable effect on the oscillations of one object from the gravity of the other, do you think that it would be practical to use observations of brightness to spot non-transiting exoplanets around other stars? So I think those are closely related.
Yeah, those are both great questions. So do planets excite oscillations in stars? I think the answer is yes, but usually those oscillations are at such small amplitude that we have no hope of seeing them. So for instance, in our own solar system, Jupiter is really far away from the sun, right? And same with the Earth. Plus the masses of the planets are tiny compared to the mass of the sun. So that means the gravitational force exerted by the planet on the star is super tiny, and the levels of those oscillations would be well below 1 part per million, I think. And so basically we can't observe them. All the binary stars I showed you that are making each other oscillate, those are usually two stars of comparable mass that get within just a few stellar radii of each other when they pass close to each other. Whereas even Mercury is at, I don't know, what is it, 40 times, no, I think it's even more than that. I think it's like 70 times the radius of the sun or something like that. So even Mercury basically is much further away from the sun than the binary stars that I showed you. So that's why they actually perturb each other to a large enough amplitude that we can see it. So yeah, so I think we can't find planets quite like that. It turns out that planets that orbit really close, so there's some hot Jupiters, which are like, Jupiter mass planets that orbit within a few days. There are a couple of those systems where the planet is mass enough and it's close enough to the star that it does actually tidally distort the star. And we can actually see that in a couple cases. Those are usually a little bit different from the oscillations I was showing you. Those are basically where the star just has a gravitational bulge that's excited by the planet that basically always tracks, it's always pointing straight at the planet. So it's not quite the same as the oscillations I was showing you before. But we have seen that effect, I think, in a couple systems. Usually the bigger effect is that the star, some of its light gets reflected by the planet. And so that also creates a photometric modulation as the planet orbits. But yeah, both effects are there.
I'd say that when reflected starlight is the bigger effect, that tells you something.
It's just the planets usually have, their mass is so low that they don't gravitationally distort the star very much. Yeah, but what was I going to say? Yeah, we have, there are a few systems where we've seen that. With binary stars, it can be very prominent. That can cause the stars to change their shape so much that those brightness fluctuations are 10 or 20%.
Okay, well, thank you. That was a great answer. Okay, next we have a couple questions about kind of more exotic systems. So here's one. Yes, so this one comes from David on Facebook, who asks if you could observe similar waves in accretion disks given enough photometric accuracy.
Yes, you can. That's a good question. People have observed these kinds of waves in accretion disks. And that's a big part of the X-ray community, is they'll take X-ray observations of accretion disks around neutron stars and black holes, and we see basically distortions of the accretion disk. They're usually called quasi-periodic oscillations. And we know that those are due to warps and bending of the accretion disk. But it's usually not quite as precise of a process because the accretion disk is not this nice kind of almost static structure. It's this very dynamic thing where everything's moving around at very large velocities. Usually those oscillations, they aren't as coherent. That's why they're called quasi-periodic instead of just periodic. And so also the math, I think, is more difficult in that situation, so they're harder to interpret. But people are working on that and trying to understand what that's telling us about the accretion disks around those objects.
That's great. Thank you.
Yeah.
Okay, next question. This one comes from Pablo Lewin, who asks, have you tried to apply this process to FRBs? So I think that would be fast radio bursts.
Yeah, no, I haven't thought very much about that. It turns out what we're learning, we've just learned in the last couple of years, is that some fast radio bursts are sort of quasi-periodic, in the sense that I know there's one repeating fast radio burst source that it doesn't repeat every 16 days, I think, but it's like there are activity windows that kind of recur every 16 days. And so that might be telling us that the source is only beaming radio bursts towards us every 16, it's some source that has some motion at the 16-day period. I think the most promising explanation is that it's a neutron star whose spin axis is actually precessing, kind of like a wobbling football, and that it points towards us every 16 days, and then it points away from us, and then 16 days later it points towards us again. So that's not exactly the same as the oscillations I was talking about, but it does give you some kind of quasi-periodic signal. There is another fast radio burst where I think it does actually look like there was more of an actual period to it. I think it was about every 200 milliseconds, where we got kind of a burst every 200 milliseconds. That only happened, once. So it was like one span of a couple seconds, we saw bursts repeat every 200 milliseconds. And for that source, I think the most promising explanation is that that is the spin period of a neutron star. Again, it's probably not an oscillation inside of the star, it's probably the spin period. But that's a very active topic of research. We're still trying to understand what that's actually telling us.
Interesting. Thanks. Okay, next question here comes from Bradley Walter, who asks, what causes the changes in modes seen in some white dwarfs?
The changes in modes? I guess I'm not sure what you're referring to.
Okay. Bradley, if you'd like to clarify that question and say more specifically what you're referring to, please do so in the Q&A box. We're going to take another question while you're doing that. So let's see. Next question here comes from Timothy Weaver, who asks, has asteroseismology been used to perform analysis on Cepheid variables, particularly in their role as standard candles?
Yep. Yeah, so there's a much longer history there because people have been observing Cepheid pulsations for more than 100 years. So Cepheids are usually quite simple in the sense that they only oscillate in one or two frequencies at a time. And those are kind of some of the simplest oscillations. They're radial oscillations. And they're kind of the lowest frequency possible radial oscillations. And you can do some seismology with that, and you can model the stars and put some constraints on the stellar structure. But because you're usually only getting one or two notes, you can't do the very detailed analysis that I was talking about that you can do for red giants, because usually what we use is kind of patterns of oscillation frequencies. One oscillation frequency by itself is usually not very useful. But if we can measure patterns, then that's where we can really learn something about the stellar interior. And Cepheids don't give us those kinds of patterns. So you can place some constraints, and people have done that and sort of verified our basic picture of the stellar structure of those stars, but you can't get very detailed pictures of the interior. One thing that has happened recently with Cepheids is with space-based photometry, people have started detecting smaller amplitude oscillations that are more like a few parts per millimagnitude. And we think those are actually due to non-radial pulsations of Cepheids. And you can, I think, do a little bit more if you add that in. I'm not aware of any results that have come out of that. But you could probably make slightly more complicated or detailed models using that extra pulsation. Again, it's only like one pulsation mode. It's not 100 pulsation modes.
Right. Okay, that makes sense. Thank you. Okay, so next question here comes from James Gage, who asks, can a star's volume act as a Helmholtz resonator and physically amplify the vibrations?
So I don't know what a Helmholtz resonator is, but I will say that the stars themselves can resonate or excite their own oscillations. So some stars like the sun, what's basically happening is you have convection, and that's causing the star to kind of shake around. But if you turn the convection off, the oscillations would eventually die down. But there's other types of stars that have self-excited pulsations, like Cepheids, where they basically have a heat engine process that causes the oscillation amplitude to grow up to some threshold at least. So there's lots of different types of pulsating stars that do that. There's ones called Gamma Doradus stars, there's Delta Scuti stars, there's Cepheids, there's RR Lyrae stars, and the list goes on. There's ZZ Ceti stars. There's many different types of stars that do that. And sometimes those are radial oscillations, sometimes they're non-radial oscillations. Almost all the time it's a heat-driven mechanism where basically the pulsation itself is able to basically capture some of the heat coming out of the star and turn that heat energy into kinetic energy of the pulsation. That's how those oscillations are usually excited. There might be a couple cases where the mechanism is a bit different from that, but you could think of that as a resonator that's exciting itself by harnessing the thermal energy of the star.
Okay, thank you. Oh yes, and James Gage, while you were answering his question, did submit a comment to say that by Helmholtz resonator, he meant the tube under a xylophone bar. So there we go.
The tube under a xylophone bar. I see. So that's basically capturing the oscillation of the xylophone key and kind of re-radiating it. I'd have to think about that. One thing I'm thinking about is if you had a binary star, could one star kind of pick up the oscillation of the other star? And actually I've done some work on that. It's possible that the oscillation of one star can actually affect the orbits of the system. But I'm not aware of any case where one star actually makes the other star vibrate. But I think in principle that could happen if you had a close binary star.
Okay, thank you. James Gage says your answer was perfect. Thank you. Okay, now Bradley Walter did come back with a bit of a clarification to his question. So we're going to go back to that. He had asked what causes the changes in modes in some white dwarfs? And as clarification, he said some pulsation periods appear and then disappear and then reappear again. And he gave the example of the white dwarf GD358.
Okay, yeah, there are, this happens with other types of stars too, especially these ones that have self-excited oscillations, where you'll see one pulsation mode at a certain amplitude and then eventually it will disappear and then it might come back again. Or you might see kind of gradual changes in the amplitude and phase and frequencies of the oscillation modes. And I don't think we totally understand that. We know that it's related to the fact that once an oscillation gets a large enough amplitude, there start being what's called nonlinear effects.
Mhm.
And so at that stage, basically the oscillations actually interact with each other. Right, so you could think of this as each oscillation is like a pendulum. And if you have a bunch of pendula swinging, they won't, they can just swing at their own frequencies. But if the pendula are actually interacting with each other somehow, like you tie a string between the pendula, then they're going to have to start affecting each other. And so one pendulum might swing at a higher or lower amplitude depending on its interactions with the other pendula. So that's kind of what the oscillations of a star are doing. Once they reach large amplitudes, they all start affecting each other. And this can cause amplitude and frequency modulations. So I think that's what's probably happening with the mode changes in white dwarfs. But in some stars, we see that, and in some stars, we don't see it. And I don't think we totally understand why.
Okay, thank you. That's another good answer. Next question is from a user on Facebook who asks if the breaking index of pulsars is compatible with gravitational radiation.
Yeah, so the breaking index is basically you measure the spin rate of a pulsar, but then you can also measure that the spin is changing over time. And it basically, the breaking index basically tells you how much the spin of the chain, how fast the spin is changing as a function of the spin period. And it's some power law, and that's the breaking index. And that for kind of simple dipole radiation, I think is expected to be 3. When you actually measure that breaking index, it's more like 2.5 or something for most pulsars. So we don't think it's due to gravitational waves. We're pretty sure it's just due to electromagnetic processes that are happening. Also with most pulsars, basically they're, a typical pulsar that's rotating at 1 second, it's rotating far too slowly for gravitational wave emission to actually be an efficient way of spinning it down. For some of the pulsars that rotate extremely fast, people are trying to see if they might actually be spinning down by gravitational radiation. There have also been searches with the LIGO instrument to actually detect gravitational waves from those very rapidly rotating pulsars and see if that could be spinning them down. There have been no detections from gravitational waves, and I'm not aware of any pulsars that have a breaking index that is more consistent with gravitational waves than kind of the ordinary pulsar emission mechanism. But people are looking for that kind of signal, definitely.
Okay, thank you. And next question, this one comes from David on Facebook. He asks, although we haven't seen the first stars yet, would they theoretically have the same kind of pulsations and behaviors?
To some extent, yes. So a lot of the physics I talked about will apply to the first stars as well. So they could definitely oscillate in many of the same ways. There is some important differences, which is that the composition of the first stars was different, right? They were basically just hydrogen and helium. There weren't any other elements like iron and oxygen and carbon and things like that. And it turns out those other elements like iron, even though they're trace elements for a star, that's only like 1% of the sun's mass. It turns out those other elements have a big effect on the structure of the star because of their opacity. Those other elements are better at absorbing light. And what that actually means, it turns out that most of these pulsations that are driven, like the delta Scuti oscillations and the Cepheids, all that kind of stuff, a lot of those pulsations are driven by the opacity of group of elements like iron. And so some of the types of pulsations that we see in stars in the local neighborhood would not be able to exist, or well, they would not be able to be excited in those first generation stars, which don't have the heavier elements. I think Cepheids are actually driven by a helium opacity mechanism, if I remember correctly. So those, I think, in principle, could exist in the first stars. And most of the Cepheids and RLI rays that we see actually are low metallicity stars that have much less heavy elements like iron than the sun. So I think a lot of those pulsations could still exist in the very first stars.
Thank you. Okay, so I know that you've kind of grazed on the answer to this question a couple times before, but we're still getting similar variants come in. So this one is asking as a follow-up for when you're making observations and measuring astroseismic activity. So this attendee says, with the exception for really large and close stars like Betelgeuse, all stars appear to all telescopes as point sources. So how are you measuring hot and cold spots on the surface of the star?
Yep, it's just because we can't see the actual spots. All we can measure is the brightness of the star.
Mm-hmm.
So what we measure is you have to integrate over the surface of the star, including both the hot and the cool spots. And that changes the overall brightness of the star. And that's what we actually measure. And like I said, there are some stars where you have both a hot and a cool spot at the same time, and those cancel each other out. And so you don't get any net brightness fluctuation. And in that case, we cannot see it. And that's why we can't see the kind of more complicated geometric patterns where you have a bunch of hot and cool spots all over the surface of the star, because those cancel each other out, and so we get no net brightness fluctuation. The sun is basically the only type of star where we can see that effect, because we can actually resolve the surface of the sun.
Right.
But for all the other stars, usually we're just measuring the net brightness fluctuation, just like how many photons we get per second. That's basically what we're measuring.
Okay, thank you. Thanks for that clarification. So next question here, this one comes from Bob Buckheim, who says, you showed an example of a star which had a rapidly spinning core and a slowly spinning surface. It seems as though this should damp out quickly to something that's more like solid body rotation. What keeps that rotation rate contrast in place?
Yeah, great question. So this is one of the things that my research has really focused on over the last few years.
Mm-hmm.
So the short answer is it's research in progress. We don't totally understand it. We know that there can be significant amounts of differential rotation in stars because we have measured it now, which is very different from a planet like the Earth. Of course, if you have a solid object like the Earth, it has to rotate as a rigid body, right? But once you have a fluid object, and especially a gaseous object, you can have different parts of the star rotate at different rates. And we don't really understand the frictional processes that damp out that differential rotation. So that's one of the things that I have been studying for the last few years. We think that magnetic fields are very important for affecting that differential rotation, and that will damp it out eventually. But there's kind of competing processes. And one thing that happens is typically as stars evolve, their cores tend to contract and get smaller and smaller as they evolve. And their envelopes tend to expand and get bigger and bigger. And by conservation of angular momentum, any part of the star that contracts is going to start rotating faster. And any part of the star that expands is going to start rotating slower. So stars very naturally will develop differential rotation where the inner part of the star rotates faster than the outer part. And then the thing that we don't understand very well is how the frictional processes in the star try to damp out that differential rotation and return it to a state of rigid rotation. And we think that magnetic fields are the most important agent for that, but we don't totally understand it.
That's interesting. Thank you. Okay, next question. This one comes from Jose Ribeiro, who asks, are all pulsations periodic, or are there some that are stochastic events? I hope I said that right.
Yeah, so I guess it's kind of a question of semantics. So all pulsations are periodic, but they may not, their quality factor, in other words, how long they stay periodic, can vary a lot. So as an example, in some pulsating stars, we see one stable frequency that will be stable. It will return in phase for as long as we can measure, right, for decades. But we'll see other stars where the pulsations come and go on a much shorter time scale. So for instance, in the red giants, the lifetime of the pulsations, in other words, how long they stay in phase, is typically something like 20 days. So the star will oscillate with a period of maybe a couple hours, and it will stay stable for maybe 20 days, but then eventually the phase will wander. So that is a stochastic process in the sense that the amplitudes and the phases are kind of only staying stable for periods of a few weeks at a time. But that totally depends on the star. Like I said, sometimes the pulsations are very stable, and sometimes they come and go on even shorter time scales of just a few oscillation cycles.
Okay, thank you. Okay, next question here comes from Mike Gardner, who asks if you can speak about the stellar corona temperature as a result of solar seismology.
Okay, well, I guess I'll start by saying, there's a big problem with the stellar corona, which is that it's extremely hot. It's like 1,000,000 Kelvin. It's much hotter than the surface of the sun, and even hotter than some parts of the interior. And we don't totally understand that. We think that the main reason is that there are waves that get transmitted up into the atmosphere of the sun that carry energy, and then those waves damp out in the corona, and so they deposit that energy as heat, and so the corona gets heated up. And the surface of the source of those waves is probably basically the same thing or closely related to the oscillations that excite the global oscillation modes of the sun. So in other words, there's convection near the surface of the sun that excites sound waves that propagate through the sun that we use for helioseismology, but it can also excite sound waves that go out into the corona, that heat up the corona. And there the physics gets complicated by the fact that the magnetic field becomes very important in the corona. So it's not just sound waves, but you also have Alfvén waves that travel along magnetic field lines. And the physics of that gets much more complicated, and it's also, of course, related to things like magnetic activity that can excite Alfvén waves. And so I'm not an expert on that process. There's a lot of people who are studying that, but I think that's the basic idea, is that you have waves going out into the atmosphere instead of bouncing around inside of the sun.
Very interesting. Thank you. Okay, we have just one more question left here. And that is, if you had to choose TESS versus Kepler, which is your favorite?
Well, that's a tough choice. I think Kepler is very near and dear to my heart. It has produced, I think, the most spectacular astroseismic data so far. But TESS is still young, it's still flying, it's still collecting data. I think by the time it's finished, it might end up being more useful than Kepler was. But Kepler really started a revolution. I mean, we really went from almost nothing. All these oscillating stars and red giants, almost none of them we could do from the ground because the amplitudes were too small. And then just kind of over the course of a couple of years, Kepler just radically altered the situation. So that made a huge influence both on the field and on my own life. And so it's hard to not choose Kepler, although I think as TESS takes more and more data, it's going to keep flying hopefully for several years, and it will build up a lot of data for more stars and also for stars that are closer and brighter, so that amateurs can do follow-up, so that we can do other kinds of measurements like measure the spectra of the stars better. So we can do all kinds of other measurements with the TESS stars, because the TESS stars are brighter on average. So I do think that will also be very powerful, but we're sort of just starting to get there in terms of the asteroseismology, because it takes usually a few years to build up enough data. And so TESS is just starting to get to that level.
Okay, well, thank you. Looks like that was our last question. So I'll go ahead and begin with the closing announcements. And the most important announcement, as always, is a heartfelt thank you to you, Professor Fuller, because this was a fantastic presentation and an excellent Q&A. And we really appreciate you sharing your time and your knowledge with us today. So thank you.
Yeah, thank you all for coming.
me get my screen share going. Okay. I would also like to thank again our sponsors, Boyce Astro and Chroma Technology. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please do check out their webpage to learn more about their work. Founded in 1991 as a 100% employee-owned company, Chroma Technology is a leading manufacturer and OEM supplier of highly precise optical filters using thin film coating technology. Their reputation is built on dedicated customer service, including free technical and application support. They remain committed to serving both the scientific and technical communities in their pursuit of the scientific endeavor. Chroma's product portfolio provides solutions for industries ranging from the life sciences and agriculture to manufacturing, inspection, security, and aerospace. The broad array of applications served include fluorescence microscopy, flow cytometry, biomedical instrumentation, surgical devices, machine vision, multispectral imaging, and of course, astronomy. You can see the links to visit both of our sponsors' websites up there on the slide. I would also like to make a special announcement to give a huge thank you to everyone who donated to support the AAVSO during our annual campaign. Thanks to your contributions, we were able to reach our campaign goal of $100,000 and to qualify for our $20,000 matching grant. Your donations are what allow us to continue to do great things for the variable star community worldwide. You make this possible. Thank you.